All right, so in the last lecture, part two of this playlist, I talked about the sum product algorithm, which produces the marginal probability. We have three main problems. What is the marginal probability of a graphical model? What is z? Calculating z is difficult because it is denominator. It is the partition function. It's even in terms of computational complexity. It is even harder than marginal probability. And the third one is this lecture, which is the max sum. What is the maximum probability of a probability function? What is a maximum achievable configuration? And we call it the max assignment problem. A max assignment problem. Map assignment problem. A map stands for maximum posterior. You know it from statistics and machine learning. What is map? So this is with the same analogy, we call it map assignment. And the algorithm that we use for this map assignment is, one of them is max sum algorithm. And so max sum algorithm is very similar to sum product because we can just replace all of those things, sums, with the maximum, and so they are very related. So finding a setting of a variables that has the largest probability and to find the value of that probability, these can be addressed through a closely related algorithm called the max sum, which can be viewed as an application of dynamic programming in graphical models. So we don't want to use brute force to find this maximum. We can do that for a small number, but we don't do it in practice. In practice, as I said, we always use dynamic programming. So we want to see what is the maximum of this probability. And the maximum is P of max. So we use these tricks. Maximum of A, B, and AC is A, maximum B, C. It's transparent from elementary school. And this one as well, the maximum could be separated. This is another trick that we use. And by combining them, we can write the max of P of X as the product of these potentials. But these max goes inside. So the max, we can write this as this maximum of another things, which itself has a max. Because the reason that we do this is we are looking for some kind of recursive or some structure so that we don't recompute everything, just like variable elimination, just like bucket elimination. We don't want to recompute everything. We want to use the advantage of the hidden structure in that. So we want to move from max product to max sum. Of course, max product is another name for max sum, because if you use logarithm, then it's max. So if you see in some articles they say max sum, they are talking about the same problem. We are maximizing a probability. This is the same problem. So we take the logarithm for numerical convenience. It's easier to work with that, good numbers, just like in some problems in finance. And the max sum algorithm is as simple as this. You see, we have just maximum. Everything is very similar, look familiar. The messages goes from, summation of messages goes from xm to f, and from the factor to x, the messages from factor to x. And everything is very familiar. So we can use the maximum of messages, the sum of messages going from the factor to the node. And so we can find it. But there is an obstacle. Because we are now maximizing rather than summing, it is possible that there may be multiple configurations. of x, all of which give rise to maximum value. So which one do you choose? In such cases, this strategy can fail because it is possible for the individual variable values obtained by maximizing the product of messages at each node to belong to different maximizing configurations, giving an overall configuration that no longer corresponds to maximum. So there is a solution for this. The problem can be resolved by adopting a rather different kind of message passing from root to the leaves. So let us return once again to the simple chain, this simple chain of variable xn to xn, and each one has case states. Like this, each one has case states. But we take node xn to be the root node, and then the first phase we propagate messages from the leaf, which is this x1, to the root, and this is the root. So we propagate this. So until now, it's just the formula for max sum. And the initial message sent from the leaf node, we put it to 0, and the most probable xn can be achieved very easily. Now we need to determine the states of previous variables that correspond to the same maximizing configuration. So we do by keeping track of which values of the variables give rise to maximum state. It's very similar in its spirit to the Viterbi algorithm. So we are doing backtracking. So from the last one, we backtrack and we get so there is no problem anymore.